Right now, somewhere between 400 and 500 meters below the surface of the North Atlantic, a cylinder of steel about the diameter of a school hallway is being squeezed by 45 atmospheres of pressure, roughly the weight of 600 fully loaded school buses pressing down on every single square meter of its hull, and it is doing absolutely nothing wrong. It is sitting there, quietly, as if the ocean is not trying to murder it at all. I want you to think about what that actually means. Not in the vague, hand-wavy way that we usually absorb facts like this, where we nod and say, yes, very impressive engineering, and then move on. I want you to actually sit with it for a moment, because if you do, if you genuinely try to picture that hull and that pressure, your intuition is going to tell you something. It is going to tell you that the steel is simply strong enough to resist the water pushing in. And that intuition is going to be wrong. Not a little wrong, fundamentally, architecturally, magnificently wrong. And the real answer, the one hiding behind your wrong intuition, is one of the most beautiful things that geometry and physics have ever conspired to produce together. Let me start from the beginning, because this story has layers, and you have to peel them in the right order. When you push on something, a wall, a rubber ball, your own hand, there are two different things that can happen. The object can resist by being stiff, by refusing to move. Or it can resist by redirecting. A brick wall resists by being stiff. A mattress resists partly by redirecting. You push here, and it pushes back from everywhere else. Now, here is the thing most people get wrong about submarines. They imagine the hull is doing the first thing, just sitting there stubbornly stiff, saying no to the ocean. That image feels right, because we associate strength with toughness, with hardness, with not budging. But the ocean at 400 meters does not care about your stubbornness. The ocean at 400 meters is applying more force per square meter than almost anything you will ever encounter in ordinary life. If you tried to resist that purely through stiffness, through sheer material obstinacy, you would need a hull so thick and so heavy that the submarine would sink before it ever dove. The actual answer involves something far more elegant than strength. It involves a shape. Now, I need to tell you something about circles that took humanity an embarrassingly long time to fully appreciate. Pick up an egg, a real egg, not a plastic one. Hold it between your fingers with the tips pressed against the two ends, the pointed end and the blunt end, and squeeze harder. You can put quite a lot of force on that egg before it breaks, and it feels wrong. It feels like you should be able to crush it easily, because the shell is only a millimeter or two thick. Why does it not break? The shell is not strong. The shape is strong. What happens when you squeeze the two ends is that the curved surface of the egg converts your compressive force, the squeezing, into tension, distributed along the curve of the shell. The shell is not being crushed. It is being stretched, very slightly, along its surface. And materials resist stretching far better when the load is spread evenly across them than when it is concentrated in one place. The arch is doing the work, not the material. The geometry is the engineer. This is the first real idea I need you to carry with you. A curved surface under uniform pressure does not experience the pressure as a crushing blow. It experiences it as a stretching along its own skin. And if the curve is a perfect circle, a cylinder, or a sphere, that stretching is distributed with extraordinary uniformity. Every bit of the surface shares the load equally. No single point bears more than any other. The ocean pushes in from all sides simultaneously, and the circle says, quietly and without drama, I distribute this. I will share this load among every atom of my circumference, and no single atom will be overwhelmed. Now, this is already not obvious, and I find it interesting that it is not obvious, because it means the visual intuition we carry around, the intuition that flat and thick is strong, and curved and thin is fragile, is exactly backward in this situation. The submarine hull is thin compared to its diameter. A modern submarine hull is somewhere between 50 and 100 millimeters of high-strength steel wrapped around a pressure vessel that might be 10 meters across. That is a thickness-to-diameter ratio that would seem insane if you tried to make a flat plate the same size withstand the same pressure. A flat plate of those dimensions at those pressures would buckle and fold like tinfoil. The curve is doing what no amount of flat steel could. But stay with me, because here is where it gets stranger. Because if the circle is so perfect at distributing load, why does anything ever implode? Why does the hull of a submarine, a beautifully circular cylinder, ever fail? If the geometry is doing all this heroic work of sharing the load, what eventually overwhelms it? This is where the second layer appears, and this layer has a name that sounds almost too simple for what it conceals. It is called buckling. Let me describe buckling to you in a way that does not require any mathematics, because the mathematics is beautiful, but the idea precedes it. Imagine you have a long, thin rod, a ruler, say, or one of those old-fashioned drinking straws before they made them thick. Hold it vertically and press down on the top end. If you press gently, nothing happens. Press a little harder, still nothing. But then, at some critical load, and this is the strange thing, the rod suddenly snaps sideways. It does not gradually bend. It does not slowly deform. It holds and holds and holds. And then all at once it catastrophically decides to go sideways. This is buckling. It is not a gradual failure. It is a sudden, catastrophic, all-at-once collapse that happens when the load crosses an invisible threshold that the geometry of the structure has set. Now apply this to a cylinder. A cylinder under uniform external pressure, like a submarine hull, is experiencing something analogous to our ruler. The cylinder is resisting beautifully, distributing load, sharing the burden, doing everything right. And then, if the pressure rises past a critical value, or if there is a tiny imperfection in the circularity of the hull, a tiny flat spot, a tiny deviation from perfect roundness, the cylinder can suddenly and completely lose its ability to distribute. It ceases to be a circle and becomes something else, and whatever it becomes has much worse load-sharing properties, and the pressure that was being handled so gracefully a moment before is now being concentrated, and the whole thing collapses inward in a fraction of a second. This is what an implosion actually is. It is not a slow cave-in. It is not gradual. When a submarine hull fails at depth, the inward collapse is so fast, happening in perhaps a millisecond, that the water rushing in hits the opposite wall and creates a shock wave that bounces back outward. The implosion generates its own explosion. And this happens not because the steel gave up, but because the geometry gave up. Because the circle for one instant allowed itself to become slightly not a circle, and that was enough. Here I want to tell you about Leonhard Euler, because Euler is one of the most remarkable humans who ever lived, and he discovered the mathematics of buckling in 1757. Think about that date, 1757. There is no steel. There is no industrial engineering. There are no submarines. Euler is just sitting there blind in one eye, eventually blind in both, and he is thinking about columns. Why do columns fail? He derived the formula for the critical load at which a slender column under compression will suddenly buckle, and that formula, Euler's buckling formula, is still used today. It is used by the engineers who designed the exact submarines we are talking about. Euler never saw a submarine. He barely saw anything. He derived, through pure thought and pure mathematics, a law that governs the structural fate of underwater vessels 2 centuries later, and he did it because he found the question interesting. What Euler found is this: the load at which buckling occurs depends not primarily on the strength of the material, but on the stiffness of the material and the geometry, specifically on something called the second moment of area, which is a way of describing how the cross-sectional shape resists bending. And the critical thing is that this critical load scales with the inverse square of the length. Make your column twice as long, your critical buckling load drops to a quarter, not to half, to a quarter. The geometry is more powerful than the material. A shorter, stubbier column can carry far more load than a longer, slimmer one made of exactly the same steel. This is why submarine pressure hulls are divided into compartments with internal frames, ring stiffeners. They are called that effectively shorten the unsupported length of the hull between supports. Not to make the hull stronger, exactly. To make the geometry smarter. Now let me zoom back out for a moment, because I have been talking about submarines and I want to make sure you feel what is really happening here. Because what we are actually talking about is not engineering at all. What we are actually talking about is the nature of pressure itself. Pressure is one of those words we think we understand because we use it every day. You talk about tire pressure, blood pressure, high pressure situations, but the physicist's definition of pressure is much stranger and more beautiful than any of those uses. Pressure, in the physics sense, is not a push in one direction. Pressure is the same push in every direction simultaneously. This is the key thing. A gas in a container does not push preferentially on one wall. It pushes on all walls equally. And the water at 400 meters below the surface does not push down on a submarine. It pushes on the submarine from every side, top, bottom, and everywhere between, all at once, all with the same force per unit area. This was not obvious to people, historically. The man who made it explicit, made it into a law, was Blaise Pascal in the 17th century. Pascal's principle, as we now call it, says that in a fluid at rest, pressure is transmitted equally in all directions. If you increase the pressure at any one point in a fluid, that increase propagates instantly and equally to every other point. You cannot have a high-pressure region next to a low-pressure region in a static fluid. The fluid will simply rearrange itself until the pressure is uniform. This is why the ocean at 400 meters has the same pressure, whether you are measuring it from the north or the south or below or above the submarine. The ocean does not care about your orientation. The ocean is an isotropic pressure machine. And here is where I want to connect this to something deeper, because Pascal's principle is not just a fact about fluids. It is a consequence of something much more fundamental, the conservation of energy and the symmetry of space. A static fluid has no preferred direction. Space itself, in ordinary experience, has no preferred direction. There is no up that is cosmically different from sideways. And because there is no preferred direction, pressure in a static fluid cannot have a preferred direction. The physics is mandated by a symmetry, not by some special property of water. If you lived in a universe where space had a preferred direction, where some directions were physically different from others, you would not have Pascal's principle, and the submarine hull problem would be completely different. The fact that our universe is rotationally symmetric is the reason the circle is such a perfect engineering solution. The geometry matches the physics of space itself. I find this genuinely astonishing every time I think about it carefully. The circular cross-section of a submarine hull is optimal not because engineers decided circles are nice, but because the physics of pressure has the same symmetry as the circle. You are matching a geometric shape to a property of space. The submarine is not just a machine. It is a physical argument made in steel that space is rotationally symmetric. Every time it survives a dive, it is confirming a deep truth about the universe. Let me give you the second thought experiment now, because I think it will make the buckling thing much more visceral and real. Take an empty aluminum soda can. Hold it in both hands. Try to crush it from the sides. Press your palms against the curved surface. You can barely do it. The can is remarkably strong. The thin aluminum curve distributes your force and resists beautifully. Now take that same can and make a tiny dent in it. Just press one finger in slightly, not enough to puncture it, just enough to create a small flat region, a slight deviation from perfect roundness. Now try to crush it again. It fails almost immediately. The tiny imperfection which seemed negligible has destroyed the geometric advantage completely. The load that the perfect circle was distributing across its entire circumference is now being concentrated at the edges of the dent, and those edges fail. This is exactly what submarine engineers spend their careers worrying about. Not whether the steel is strong enough. The steel is strong enough. What they worry about is circularity. How close to a perfect circle is the hull at every cross-section? Because even a deviation of a few millimeters from perfect roundness in a hull 10 meters in diameter, we are talking about something like 1 part in 1,000, can drastically reduce the pressure at which buckling occurs. The tolerances in submarine hull construction are not engineering conservatism. They are geometric necessity. They are the direct physical consequence of the fact that the circle's load-sharing ability depends on the circle being an actual circle, not approximately a circle, not mostly a circle, a real circle, maintained with obsessive precision across every meter of the hull's length. The way this is handled in practice involves something called the von Mises yield criterion, after Richard von Mises, who derived it in 1913. Von Mises was trying to answer a question that seems simple but is not. when does a material fail? Not when does it crack, but when does it begin to permanently deform, to yield, to give up its elasticity. And what he found is that materials do not yield based on any single stress, not based on how hard they are being pushed in one direction alone. They yield based on a combination of all the stresses they are experiencing simultaneously in all directions. There is a formula, the von Mises stress, that takes all the different directional stresses and combines them into a single number. When that number exceeds the yield strength of the material fails. Not before, not based on any individual component alone. Why does this matter for submarines? Because the hull is being stressed in multiple directions simultaneously. It is being compressed around its circumference hoop stress, it is called, and it is being compressed along its length and axial stress, and it is being bent and sheared by the frames and by any asymmetry in the loading. The hull does not fail when any one of these stresses exceeds a threshold. It fails when their combination, as computed by von Mises, crosses the line. So the engineer cannot simply say, the hoop stress is below the yield strength, we are safe. The engineer must compute how all the stresses interact, because the failure of a submarine hull is not a story about one force. It is a story about forces conspiring. Now, I said I would tell you one honest moment of uncertainty, one place where the physics does not have a clean answer, and I want to keep that promise. Because here is the thing about buckling. We know the critical load at which a perfect cylinder buckles under uniform external pressure. Euler and his descendants Timoshenko, Windenberg, Trilling, and others worked out the mathematics with great precision. For a perfect cylinder, the theory is beautiful and complete, but real cylinders are not perfect. They have imperfections. And the relationship between those imperfections and the actual buckling load is even today not fully understood. What the experiments show is deeply unsettling to anyone who thought the theory was finished. Real cylinders buckle at loads that can be 30 to 60% lower than what the perfect cylinder theory predicts. 30 to 60%. That is not a small correction. That is the theory being wrong by almost half in the worst cases. And we know why it is wrong in broad terms. It is because of the imperfections, the tiny deviations from ideal geometry. But we do not have a clean general theory that takes an arbitrary imperfection and tells you exactly how much it will reduce the buckling load. We have numerical simulations, we have experimental data, we have engineering safety factors that are large enough to cover our ignorance. But we do not have the complete theory. This is not a failure of physics. I want to be clear about that. This is physics being honest. The full problem, a real cylinder with real imperfections under real loads, is a nonlinear problem of extraordinary complexity, and nonlinear problems are where the universe gets genuinely devious. Most of the physics you learn in school is linear. Twice the input gives you twice the output, and you can add solutions together. The real world is mostly nonlinear. And nonlinear systems can have behaviors that are qualitatively different from what any linear approximation predicts. Buckling is one of these. The geometry of the failure depends on the history of the loading, on the precise spatial pattern of the imperfections, on interactions between different buckling modes that are nearly impossible to fully characterize. The engineers handle this through extensive testing and through conservative design margins, and the submarines are safe. But the complete theory is still being worked on. There are still graduate students right now spending their lives on exactly this problem. And I find that wonderful, not embarrassing. Let me now talk about what happens inside the steel itself, because I have been talking about the hull as if it is a smooth geometric surface, but it is made of atoms, and the atoms matter. High-strength steel, the kind used in submarine pressure hulls, HY80 or HY100 or the more modern grades, is not just iron. It is a carefully engineered crystal structure, alloyed with nickel and chromium and molybdenum, heat-treated and tempered to produce a microstructure that can absorb enormous energy before failing. The HY stands for high yield, which means the material can be stressed to very high levels before it permanently deforms. HY80 yields at about 80,000 pounds per square inch, roughly 550 megapascals. That is a phenomenal stress capacity. But The interesting thing from a physics perspective is not the yield strength alone. It is the relationship between yield strength and toughness. Toughness is the ability of a material to absorb energy before fracturing, to deform, to accommodate stress concentrations, to not crack catastrophically. And here's the uncomfortable truth. As you increase the yield strength of steel, as you make it stronger, you generally decrease its toughness. There is a fundamental trade-off in materials science between strength and toughness. Making a material harder to permanently deform tends to make it more brittle, more prone to sudden fracture when a crack starts to propagate. The art of submarine metallurgy is riding this trade-off, getting as much yield strength as possible while maintaining enough toughness that a small crack does not immediately propagate through the entire hull. This trade-off is not arbitrary. It has a physical origin in the behavior of dislocations, line defects in the crystal lattice of the steel where atoms are slightly misaligned. When you stress a piece of steel, it is these dislocations that move, and their movement is what allows the steel to deform plastically rather than fracturing. A material that deforms plastically before fracturing is tough. A material with very few mobile dislocations, which is what high-strength treatment tends to produce, is strong but less capable of accommodating stress through deformation, and fracture becomes more likely. A submarine hull is, at the atomic level, a carefully choreographed balance between dislocations being immobile enough to resist yield and mobile enough to absorb energy before fracture. This brings me to a historical moment that I think is underappreciated, and it is a moment that connects submarine engineering to the deepest physics. In the early 20th century, when submarine design was becoming serious engineering rather than adventurous tinkering, engineers used the yield strength as their primary safety criterion. If the stresses in the hull were below yield, the hull was considered safe. If they exceeded yield, it was considered failed. Simple, clean, wrong. What they discovered, sometimes tragically, is that hulls could fail at stresses well below yield through a process called fatigue. Fatigue is what happens when you apply a stress repeatedly, cycling between loaded and unloaded states. And over time, over thousands or millions of cycles, small cracks initiate and grow, even though at no single moment does the stress exceed what the material should be able to handle. Submarines dive and surface repeatedly. Each dive cycle subjects the hull to a full pressure loading and unloading, repeated hundreds of times over the life of the submarine. The hull must not only survive each individual dive, it must survive the accumulated fatigue of all the dives across its entire operational life. The physics of fatigue crack growth was put on rigorous mathematical footing by Paul Paris in 1961, in a paper that initially had enormous difficulty getting published because reviewers did not believe the result was as clean as Paris claimed. What Paris showed is that the rate at which a fatigue crack grows per loading cycle depends on a quantity called the stress intensity factor, which captures both the magnitude of the stress and the geometry of the crack raised to a power, and that this power law relationship holds across an enormous range of crack growth rates and material types. The Paris law, as it is now called, is one of those beautiful empirical regularities that turns out to be deeply connected to the fracture mechanics theory that Griffith and Irwin had been developing in parallel. It gave engineers a way to predict, given the initial size of a defect, the loading cycles, and the material properties, how many cycles a structure could survive before the crack reached a critical size and caused fracture. This matters enormously for submarines because it means inspection intervals are not arbitrary, they are calculated. The engineers know, or believe they know, with the appropriate uncertainty built in, how fast any given defect will grow under the expected loading history, and they schedule inspections to find it and fix it before it becomes a catastrophic crack. The submarine's safety is not just a property of the steel it was built with. It is a property of the steel, plus all the inspection history, plus the operational record, plus the accumulated fatigue damage that is being tracked, cycle by cycle, throughout the vessel's life. Now I want to pull back one more time, further than before, and ask something that might seem philosophical but is actually deeply physical. Why does pressure increase with depth in the first place? This seems obvious. The water above is heavy, and it pushes down. But the physics is subtler than it appears. The pressure at any depth in a fluid is equal to the weight of the fluid column above that point divided by the area. This is called hydrostatic pressure. For seawater, the pressure increases by roughly 1 atmosphere 100,000 pascals for every 10 meters of depth. At 400 meters, that is 40 atmospheres, plus the 1 atmosphere of atmospheric pressure at the surface, so roughly 41 atmospheres total, or about 4 megapascals of pressure. This is enough to compress water measurably. Seawater at depth is slightly denser than seawater at the surface, because water, despite feeling incompressible, is not perfectly incompressible. It has a bulk modulus, a resistance to compression of about 2.2 gigapascals, which means that at 400 meters, the water is compressed by about a fraction of a percent. Small, but real. And here is something that most people find surprising. The submarine itself is compressed by this pressure. The steel hull, the internal structure, everything. The entire submarine shrinks slightly as it dives. The diameter of the hull decreases by a small but measurable amount. The submarine at 400 meters is physically smaller than the submarine at the surface. Not much smaller, we are talking about fractions of a millimeter across a 10-meter diameter, but smaller. And this has practical consequences. The geometry of equipment bolted to the hull, seals and fittings and through-hull penetrations, all of these must accommodate this slight breathing of the submarine as it changes depth. Nothing inside the submarine is truly fixed. Everything is, at some level, elastic. Everything moves slightly as the pressure changes. The submarine is alive with tiny deformations. This is, in a strange way, the deepest thing I want to say about why submarines do not implode. They do not implode because they are not rigid. They are not brittle. They are elastic, they deform under pressure, and then they return to their original shape when the pressure is released. Exactly the way a spring does, exactly the way any elastic material does, provided the stress remains below yield. The submarine's survival is not about being immovable. It is about being precisely, correctly, controllably, movable, flexible enough to deform, stiff enough to return, shaped in such a way that the deformation is distributed so uniformly that no single point is ever pushed past the yield limit. This is a general principle that goes far beyond submarines. The most durable structures in nature are not the most rigid ones. They are the ones that have learned through evolution or through engineering how to distribute stress, to flex without fracturing, to deform along predictable paths that lead back to the original configuration. Bone does this. Trees do this. The arches of ancient Roman aqueducts do this. The pressure hull of a submarine does this. The principle is the same in all of them. Load sharing through geometry, elastic deformation within safe limits, and a shape that matches the symmetry of the forces being applied. And if you want to go even further, if you want to follow this thread to its absolute end, then I will tell you that this principle shows up in places you would not expect. The same mathematics that describes the buckling of a submarine hull also describes the buckling of DNA under torsional stress in the cell nucleus. Because DNA is a thin elastic rod under compression, and it follows Euler's buckling instability just as faithfully as a submarine hull does. The same equations, a different physical scale, a different material, the same geometry. The fact that this is so that the same mathematics governs structures at scales 18 orders of magnitude apart is one of the things that convinced me that mathematics is not just a tool we invented to describe nature. It is something we discovered that nature was already using. Why should the universe be describable by mathematics at all? This is a question that people call philosophical, but I call it physical because it has a physical answer, or at least a partial one. The universe appears to be mathematically structured because the universe is symmetric. It has patterns. The same rules apply in the same way everywhere and always. When I say the submarine hull follows Euler's buckling formula, I am saying something about the universe, that the rules governing compression and elastic instability do not change from place to place, do not change from century to century, do not depend on the material or the application in any but the most controlled and systematic ways. The mathematics works because the symmetries are real. And the symmetries, as far as we can tell, go all the way down to the quarks and the steel atoms in the hull, to the quantum mechanical wave functions that determine why iron has the crystal structure it does, to the standard model of particle physics that describes why iron exists at all. So when a submarine dives to 400 meters and the hull holds when that elegant circular cross-section quietly distributes 40 atmospheres of load across its skin without buckling, it is not just a triumph of engineering. It is a demonstration that the universe is comprehensible, that the rules work, that a person sitting in the 18th century thinking about columns can derive a formula that protects sailors in the 21st century because the universe is the same universe, following the same rules. In both cases, that is the most astonishing thing to me. Not the strength of the steel, not the precision of the construction, the fact that the universe is the kind of place where understanding is possible at all. I want to close with something I have been circling around without quite saying, because we have talked about why submarines do not implode. The pressure, the geometry, the circle, the buckling, the fatigue, the elasticity, all of that is real and all of that is true. But there is one more thing. The ocean at 400 meters is dark. Completely dark, not dim, not murky, but genuinely, absolutely lightless, because the last photon from the sun gives up somewhere around 200 meters. The pressure is 41 atmospheres. The temperature is just a few degrees above freezing. The crushing weight of the water column above is not a metaphor. It is a physical fact experienced by every atom of that hull. And inside the hull, separated from that environment by 50 millimeters of carefully engineered steel, are human beings, people, with their ordinary human concerns and their coffee and their arguments and their inside jokes. People who are alive in a place that should not support life, in a vessel that is protected not by magic and not by sheer mass, but by a geometric idea, the idea that a circle shares its load. We tend to think of human civilization as something that grows by accumulation. More people, more technology, more complexity. And that is true. But the deepest things that allow civilization to exist, the things that let people survive where they should not be able to survive, are ideas, not brute force, not just material. Ideas about geometry, ideas about symmetry, ideas about how forces move through structures, ideas derived by blind mathematicians in the 18th century, by metallurgists thinking about dislocations, by engineers staring at failed pressure vessels trying to understand exactly where the theory broke down. A circle under uniform pressure shares its load. That is the idea. It is almost embarrassingly simple when you state it that way. And yet it took millennia of human thought to understand it fully, to express it in mathematics precise enough to build on, to apply it with sufficient care that you can put people inside it and send them into the darkness and bring them back. That simple idea, held in a few lines of mathematics, is the difference between the ocean and the inside of the submarine, between an environment that would kill you in seconds and the space where people drink coffee and argue and do their ordinary human work. The hull is just steel. But the idea in the hull is something else entirely. The idea is a piece of understanding wrested from a universe that did not have to be understandable by people who chose to think carefully about circles. I am still amazed that it works.